So what we're looking at is this class is very simple. It's called caching. And in it, you can see that we just do a very, very simple setup. Part of the code here is controlled by this array test data. And test data is pretty straightforward. It's an array of ints. So there are just over 2 million. I've used 1024 times 1024 instead of a million, just because it's powers of 2, and it kind of makes the maths, well, if not easier, then easier for the computer. You know, humans prefer 10 bases, and computers prefer base 2. So yeah, so this is a nice even power of 2 to make life easier for the computer. So we have an array called test data. And then we jump into this class. You know, down here we've got the main method, which basically just dumps us into this run method. There's a bit of code here. You can probably see this. Don't worry about what that does. I'll explain why that's there later. And then we actually come on to the main part of the program where we print out line and item. And then what we're going to do is we're going to drop into this for loop. And this is just like the world's simplest, most boring style for loop that you can imagine. And we're going to do 100 iterations. So just from I equals 0 to less than 100. And you know what? I'm actually going to change the code a little bit here, because I actually have been writing a fair amount of Rust lately, if anyone's played with the Rust programming language. And what that has taught me is that I actually don't like the increment and decrement operators anymore. They actually are a source of bugs. So whenever I find a piece of my Java code like this, I'm actually just going to modify this, and actually, instead of saying I++, I'm actually converting this to the statement I equals I plus 1. It's clear, it's unambiguous, there are no side effects, there's no cleverness that I'm relying upon. It's just, it actually makes it, I think, easier to understand. And you know, it's kind of a good example about how when you start programming in more than one language, you know, you can actually have different techniques which come in to influence the way you write code, and it propagates back into the code you write in other languages as well. Okay, so yeah, so that's my code for the for loop. And what we're going to do is in each iteration through the for loop, you know, you can see this probably block of code here, and you can see the repeated calls to system.nanotime. Now, if you're not aware, then you maybe even know this, and maybe you don't. But with system.nanotime, you have to always have pairs of calls. You can't really make any sense out of making a call to system nanotime by itself. It just doesn't really mean anything. Yeah, because what it actually does, at least on Macs and Linux, is it reads a counter from the CPU. And when you switch your computer on, you actually don't know where that counter is initialized. It's not synchronized to the system clock, the wall clock, or anything else. It's just a random number. But no matter where it starts, it continues to increment. So every nanosecond, or every time the processor clock ticks, this counter is incremented. So you can use it to get a very high precision measurement of how much time has elapsed from a given starting point. So you put the nanotime calls in pairs like this. So like this first one here is T0. And let's just zoom in a bit. There we go. And maybe we'll just get rid of this. Clear up, we don't need the project open as well. So how's that? That's looking a bit better. So we set up T0. We call this method called touch every line. And then we also call touch every cache. And these methods are down here, which we're going to meet in a second. And then what we're going to do is we're going to time them separately. So we need to bookend each of them with these calls to nanotime to get these answers back as to how many nanoseconds each method took to run. And then we're going to get these other long values, which is EL every line and EL every item. And just by subtracting the two values from the nanotime. So pretty low level and pretty low tech. But what it's going to give us is it's going to give us the times that the every line and every item method took to run. And we're going to print out 100 of those. So I'm just going to run this, and we'll just see what happens. Starting to run. It takes a little while, and then as you can see, it runs through really quickly like this. Once it's actually got past this, because of course, you know, there was a hidden bit of code here which doesn't actually output anything. It just runs those methods repeatedly, and you might very well be able to guess what it's doing there. If you can't, then I should say that it's basically for the it's for the JIT compiler. So it's there in order to allow the JavaScript compiler to warm up fully and to actually see what's the methods as they actually are after JIT compilation. This means that the methods are running as fast as they can, and there's no inconsistency in how they're running later. If you don't warm up, then you get numbers which are not correctly calibrated, and that's generally not super helpful. Going to show us some interesting results here. So one of the things we have is that if we look carefully at every item on every line, we can see that what happens is that and again, I'm going to make my change here. I'm going to make this I equals I plus 1, and just I equals I plus 16, just to make it very clear what's actually happening. And IntelliJ's helpfully rearrange those, so let's just rearrange both of those as well. And then, let's just get rid of those increment operators, because I think I'm actually kind of overusing them, or I'm over the use of them, let's say. Yeah, so you can see that it's the same statement that is happening for each of these elements. There we go. And this one, touch every line, you see, is only incrementing. Well, it's not hitting every item. This one, which is kind of where the name comes from, it's actually incrementing every single item that's present in the array. Whereas this one is only doing every 16th element. And that's kind of a little bit strange, because what it means is that this method is only doing 1/16 of the work, right? It's only incremented a 16th of the elements of the array by the time that it reaches the end. And yet, and by the way, there's no trick here. It genuinely only does increment 1/16 of all of the elements. There's no hidden get out clause. It actually does only 1/16 of the work. But when we look at the timings, you can see several things. First of all, you can see that there is actually quite a lot of noise and jitter in these numbers, and we'll come back to that. And then the other thing that you can also see is that if this was true in the sense that we're expecting it, and every item should be running for 16 times as long, you would think. You're doing 16 times the work, well, you should run for 16 times as long. And that's not happening. Yes, there's some variance, but look, there are numbers like this one here, where they're basically running for more or less the same time. So we've got 69 and 62. We've got 56 and 50. We've got 62 and 59. And in fact, in this case, 62 and 59, this one is actually running faster. Sorry, the line is actually taking more time to run than the every item. So the every item is running faster than every line, which seems, really quite unusual and quite crazy. It's just like, well, how could that be happening? And then you can also get down and you can see that this method can run in as little as 44. I mean, let's work the units out here. So this is nanoseconds. So that's 443,000 nanoseconds, and 1,000 nanoseconds is a microsecond. So the method can run in as little as 443 microseconds, which is kind of incredible. That's a really small amount of time. But then it can also take as long as, 137. Well, that's not 137. That's 1.37 million nanoseconds, right? Now, a million nanoseconds is a millisecond. So that's 1.37 milliseconds. So roughly 3 or 4 times as long. And look, there's one down here which is even more than that. That's actually 2.14. That's 2.14 milliseconds. That's really quite a long time for such a simple little method to run. And you might say, oh, there's potentially all sorts of other things going on. Well, you might guess at things like garbage collection. And, that would be a good guess for most programs. But as you can see, I don't actually create any new objects here. at least not in these little methods. All of my object allocation is done up front. I create the array of test data. And sure, we loop over it and we modify it and we do a lot of reading and writing to memory, but we don't create any new objects. So this is also immune from the effects of garbage collection. In practice, writing these types of benchmarks is actually really, really difficult, and it's not easy to get them right. So I normally recommend that people don't try to write them themselves, and instead that people actually don't look this closely at the detail. The reason I'm doing it today is just to show you that these variations and this weirdness in the numbers really exists. So there's a lot of noise here, and there's a lot of things which can go on to cause this noise. But the big takeaway that two big takeaways really. One of them is Java performance numbers at a low level are really noisy and really messy, and you have to be careful how you handle them. That's the first takeaway. The second one is actually this puzzle, this mystery of why the numbers are so similar in the first place. It seems strange. It seems, why would you have numbers which are so similar when on paper, at least in the code, this one looks like it's doing hardly any work. Okay, well, let's explain what's actually going on here. When you ask a program to access memory, especially memory in an array like this, you don't get a single byte of memory at a time. Instead, modern hardware provides you a chunk of memory which consists of 64 bytes. So rather than just modifying a single int or loading a single int at a time for modification, you're actually getting 64 bytes of memory at a time from the silicon chips that make up your computer's memory. Okay, and that number 64 turns out to be important, because notice that I've carefully chosen the number here to be 16. And ints in Java are 4 bytes, and 16 times 4 is 64. So the trick that I'm exploiting here is that actually, even though I only increment every 16th element, I still fetch the entire array. So the hardware still has to physically respond by sending all of the data, the whole 2 meg, over the computer's memory bus. Okay, and that is basically all of the work of the program. The work of the program is not in incrementing individual elements. The work of the program is transferring the data from main memory to a place where the CPU can act on it. And that's a little surprising to a lot of people, that we can have this situation where we can, we have what looks like a much larger amount of work, and actually it's done in almost the same time, and perhaps even in more time than it takes to do less work. Now, just to show you this, I'm actually going to change the number around here. I'm going to rerun this. I'm going to put the increment up to not to 1, but to by 64. And now what's happening is we're going to miss out a few of those chunks of memory. They're called cache lines. At this point, I now don't need to actually receive every cache line for this second method, because I'm jumping ahead by 64 bytes, 64 ints each time. So that means that I only need to receive 1 in 4 of the computer's cache lines that make up the block of memory which corresponds to this array. So let's rerun this and see what happens. Now, we're expecting to see a decrease. We're expecting to see the amount of time taken to read every line to be significantly less than touch every item this time. Will it be that factor 4? Because if my theory is right, it should be about a factor 4. It's not actually going to be that. If we look carefully at these numbers, then what we can see is that every line, so the left-hand column, is, well, sometimes it's a factor 2, sometimes it's a factor 3. But in pretty much all cases, it seems to be coming in significantly less. There are some outlier points like this one where it comes in at 477 microseconds, and every item is about a factor 3 and it's quite a lot larger. But in general, there seems to be about a factor 2 or factor 3. Yeah, there's a definite signal here now. I mean, we can plot these numbers, and I've actually been playing around with a Java charting library, but we probably don't have time to do that today. But maybe on a future session, I can actually plot these numbers and just show you how noisy the data is. But even without doing the plot, you can still see that there is very definitely a signal here. There is very definitely an effect, and that changing the every line method to not receive all the data, to not require all the data to run the method, has had an impact which has substantially changed the performance characteristic of the individual method. Okay, so there's actually a picture. I've got a thing that I like to show, which I think conveys this pretty well. This is what I sometimes call my scary clown diagram. We have the eyes, which are the grey circles. They're actually the CPU cores, of course. And we also have 3 levels of CPU cache: level 1, level 2, and level 3. And those are the green, yellow, and orange levels of cache shown on the diagram. We also have the physical interconnect, which is called the North Bridge, which connects the CPU to main memory. And I've shown the North Bridge here as a dotted line. You might also be able to see, if you look closely, there are a couple of other CPUs that I've also shown in kind of a ghostly, shadowy grey color, which are also present on the North Bridge as well. That turns out to be quite important because the North Bridge is shared. It's shared between all of the CPU chips, and it's shared between all of the processing cores which are present on each individual CPU chip as well. So that means that the bandwidth of the North Bridge is a really, really important part of how the computer operates. It's actually one of the most important performance characteristics of all, and it's always surprises me how few people actually know what the bandwidth of their North Bridge is. And the reason this is so important is because if I'm going to do anything on a program, and bear in mind, we're down way deep in the hardware here. We're not talking about Java or C++ or any specific programming language. What I'm talking about here is about all programming languages. We're talking about the fundamentals of the way that a computer executes code, and we're below the language. We're below the Java virtual machine. We're below the operating system. We are down at hardware level. So a lot of what I'm saying here will also be true of other languages, of good languages, which are able to take advantage of the hardware. But the absolute hardest you can push any language in terms of, say, allocating memory or creating objects is governed by the North Bridge. You just can't push the hardware any faster than the North Bridge can go. So, for example, if you are executing code on the CPU core, which corresponds to the creation of a whole bunch of objects, well, those objects are going to be allocated in the L1 caches, and then that's going to have to flow back to main memory. It's going to have to flood back across the North Bridge. So the speed of it, the actual time taken to get those allocated objects, the ones that have been set up and prepared, across the North Bridge, that takes time. It's not an instantaneous operation. And the absolute maximum rate that you could allocate objects is determined by that speed of the North Bridge. So you might take a guess. I mean, it very, of course, now depends very much on your hardware. But on modern hardware, you would expect to be able to allocate several gigabytes per second, and that's kind of a decent benchmark. I mean, in general, I have different rules of thumb for allocation rates, and hopefully a bit later we're going to talk about Java Flight Recorder and mission control, and I'm going to show you some actual allocation rates that I have on my machine, and we can talk about points where I would start to investigate things. But in all cases, you can't beat the laws of physics. You can't beat the speed of transfer that's possible across that North Bridge. And remember, this is a shared resource. So, and not only is it shared, it's shared at the physical level. So if you have multiple virtual machines sharing the same physical infrastructure, as we do, for example, in the cloud, this is subject to noisy neighbor problems. So this is the idea that if you have virtualized containers, they still have to run on silicon. They still have to run somewhere. And if you have two applications in completely separate virtual containers, which are running on top of the same hardware, and both of them are allocating a lot, they may feel the effects of the other container that's running, because they are oversubscribing. They're trying to push too hard on that shared resource, which is the North Bridge. So this is, you can never truly, as much as we might like to, abstract away and have Docker and Kubernetes and virtual environments, that they always run on top of real computers. And those real computers have hardware resource limitations, which you can never truly get rid of. So the point of the scary clown is just to show you that the computer's hardware and its resources are also an important part of how we would think about performance.